Implicit differentiation allows us to take the derivative of an equation that's not been explicitly solved for either x or y, but still take the derivative. So suppose that I have the square root of x plus the square root of y equals 6, and I have the point 9, on the graph, and I want to find what's going on with the change in y with respect to x. I want to find this dy dx at the point 9. So I'm going to take the derivative with respect to x of both sides of the equation here. As a reminder, square roots are really the same thing as 1/2 power, so this is x to the 1/2 and y to the 1/2. This helps me to be able to use the power rule. The derivative of a constant, the derivative of 6, is just 0, so I'll simplify that right side now. To take these derivatives, I'm going to drop these powers to the front, so I'll have 1/2 x, taking 1 away from the power, negative 1/2. And I'm going to pause here for a second because what I just did is I took the derivative of a function of x with respect to x. So I looked at the derivative with respect to x of something with x. I have this dx piece. Plus, let's take the derivative of this y piece. 1/2 comes down. I take 1 away from the power. I have taken the derivative of y with respect to x. So I have taken the derivative of y dy dx. Anytime you're taking the derivative of the variable with respect to itself, that's just 1. So I have 1/2 x to the negative 1/2 power plus 1/2 y to the negative 1/2 dy dx is equal to 0. The function that I want, dy dx, is sitting right there. So let's solve for this thing. First thing I can do is I can multiply everything by 2 to get rid of those fractions. Now I can write these back in their exponent or in their radical form. So negative power, that's 1 over. 1/2, that's the same thing as the square root. So this is 1 over the square root of x plus 1 over the square root of y dy dx is equal to 0. Let's subtract that 1 over square root of x to the other side. From here, let's try multiplying both sides by the square root of y. That will cancel out the square root of y's on the left side. This leaves me with the square root of y over square root of y, dy dx, is equal to negative square root of y over square root of x. Canceling out that left side leaves me with just my derivative with respect to x is negative square root of y square root of x. We wanted the derivative of y with respect to x at the point 9. So let's plug in 9 into our function. My y value is 9. I'll plug that in for y. And my x value is 9. I'll plug that in for x. The square root of 9 is 3, so I have negative 3 on the top. Square root of 9 is 3 again, so I have 3 on the denominator. Negative 3 divided by positive 3 gives me a slope of negative 1. So the derivative of this curve at the point 9, I used implicit differentiation, which looks just like regular differentiation, but I'm adding these dx dx, dy dx. I'm adding whatever variable I took the derivative of with respect to whatever I was trying to take it with respect to. Dx dx, those things just go away. The dy dx, that's my change in y values over change in x. That's rise over run. That's my y prime. So implicit differentiation allows me to take the derivative even when y has not been solved for.